Hello there. Here at Crash Course HQ, we like to start out each day with a nice, healthy dose of water in all its three forms. It is the only substance on all of our planet Earth that occurs naturally in solid, liquid, and gas forms. And to celebrate this magical bond between two hydrogen atoms and one oxygen atom, here today we are going to be celebrating the wonderful life-sustaining properties of water. But we're going to do it slightly more clothed. Much better. When we left off here at the biology crash course, we were talking about life, and the rather important fact that all life as we know it is dependent upon there being water around. Scientists and astronomers are always looking out into the universe, trying to figure out whether there is life elsewhere, because, you know, that is kind of the most important question that we have right now. They're always getting really excited when they find water someplace, particularly liquid water. And this is one reason why I and so many other people geeked out so hard last December when Mars's 7-year-old rover Opportunity found a 20-inch long vein of gypsum that was almost certainly deposited by long-term liquid water on the surface of Mars. And this was probably billions of years ago, and so it's going to be hard to tell whether or not the water that was there resulted in some life. But maybe we can figure that out, and that would be really exciting. But why? Why do we think that water is necessary for life? Why does water on other planets get us so freaking excited? So let's start out by investigating some of the amazing properties of water. In order to do that, we're going to have to start out with this. The world's most popular molecule, or at least the world's most memorized molecule. We all know about it. Good old H2O. Two hydrogens, one oxygen. The hydrogens each sharing an electron with oxygen in what we call a covalent bond. So as you can see, I've drawn my water molecule in a particular way, and this is actually the way that it appears. It is V-shaped. Because this big ol' oxygen atom is a little bit more greedy for electrons, it has a slight negative charge, whereas this area here with the hydrogen atoms has a slight positive charge. Thanks to this polarity, all water molecules are attracted to one another. So much so that they actually stick together, and these are called hydrogen bonds, and we talked about them last time. But essentially what happens is that the positive pole around those hydrogen atoms bonds to the negative pole around the oxygen atoms of a different water molecule, and so it's a weak bond. But look! They're bonding! Seriously, I cannot overstate the importance of this hydrogen bond. So when your teacher asks you, what's important about water? Start out with the hydrogen bonds, and you should put it in all caps and maybe some sparkles around it. One of the cool properties that results from these hydrogen bonds is a high cohesion for water, which results in high surface tension. Cohesion is the attraction between two like things, like attraction between one molecule of water and another molecule of water. Water has the highest cohesion of any non-metallic liquid, and you can see this if you put some water on some wax paper or some Teflon, or something where the water beads up, like some leaves of plants do it really well. It's quite cool. Since water adheres weakly to the wax paper or to the plant, but strongly to itself, the water molecules are holding those droplets together in a configuration that creates the least amount of surface area. It's this high surface tension that allows some bugs, and even I think one lizard, and also one Jesus, to be able to walk on water. The cohesive force of water does have its limits, of course. There are other substances that water quite likes to stick to. Take glass, for example. This is called adhesion, and the water is spreading out here instead of beating up because the adhesive forces between the water and the glass are stronger than the cohesive forces of the individual water molecules in the bead of water. Adhesion is attraction between two different substances, so in this case, the water molecules and the glass molecules. These properties lead to one of my favorite things about water, the fact that it can defy gravity. That really cool thing that just happened is called capillary action. And explaining it can be easily done with what we now know about cohesion and adhesion. Thanks to adhesion, the water molecules are attracted to the molecules in the straw. But as the water molecules adhere to the straw, other molecules are drawn in by cohesion, following those fellow water molecules. Thank you, cohesion. The surface tension created here causes the water to climb up the straw. And it will continue to climb until eventually gravity, pulling down on the weight of the water in the straw, overpowers the surface tension. The fact that water is a polar molecule also makes it really good at dissolving things, which we call it's a good solvent then. Scratch that. Water isn't a good solvent. It's an amazing solvent. There are more substances that can be dissolved in water than in any other liquid on Earth. And yes, that includes the strongest acid that we have ever created. These substances that dissolve in water, sugar or salt being ones that we're familiar with, are called hydrophilic. And they are hydrophilic because they are polar. And their polarity is stronger than the cohesive forces of the water. So when when you get one of these polar substances in water, it's strong enough that it breaks all the little cohesive forces, all those little hydrogen bonds, and instead of hydrogen bonding to each other, the water will hydrogen bond around these polar substances. Table salt is ionic, and right now it's being separated into ions as the poles of our water molecules interact with it. But what happens when there is a molecule that cannot break the cohesive forces of water? It can't penetrate and come into it. Basically, what happens when that substance can't overcome the strong cohesive forces of water and can't get inside of the water? That's when we get what we call a hydrophobic substance, or something that is fearful of water. These molecules lack charged poles. They are non-polar and are not dissolving in water because, essentially, they're being pushed out of the water by water's cohesive forces. Water, we may call it the universal solvent, but that does not mean that it dissolves